Good morning. Last class we have solved numerical problem on volumetric strain, and earlier we discussed about various stresses and linear strain. Linear strains are of longitudinal strain, lateral strain and volumetric strain. So, let us introduce another strain. It is shear strain. And right now we will denote this shear strain as phi. In order to understand this shear strain, let us consider an elemental block. Elemental block A, B, C, D. Let this elemental block is subjected to shear stress along its or on its top edge, and this tau is the shear stress. As a result of this shear stress, element ABCD gets displaced to or shifted to AB dash, C dash and D, resulting angular displacement pi. You can see here. This angular displacement is known as shear strain. When an element is subjected to shear stress on the top edge or on an edge, because of this fixity at the one end and free end at the other end, the element gets displaced from their original position ABCD to AB dash C dash D. So, this angular displacement is known as shear strain, which is caused by this applied shear stress. From trigger, in triangle AB dash B, tan pi is equal to BB dash divided by AB. As displacement is very small, we can write it is as displacement is very small, tan pi is approximately equal to pi, that is shear strain. Therefore, pi is equal to BB dash divided by AB. So, this is shear strain. So, here onwards, whenever we come across this type of angular displacement, without further explanation, we can consider this type of angular displacement as shear strain, that is opposite divided by the adjacent side. Now, let us consider another important concept regarding the shear displacement. State of simple shear and complementary shear. So, in order to define this what is state of simple shear and complementary shear, let us define this in terms of the figures. Let us have again a square block. Let this square block is subjected to shear stress, a pair of shear stress on its two edges. Figure 1 can consider. Let us consider another block of same dimension and consider this as figure 2. Here this block is again subjected to shear stress of magnitude tau on two of its edge. That is, this is same as that of the figure 1. In addition to this, here the other two sides of the block subjected to shear stress of same magnitude. So, with respect to these two figures, we can easily define this state of simple shear and can easily understand what is this state of simple shear and complementary shear. As per state of simple shear, a set of shear stresses are always accompanied by a set of complementary shear. So, a set of shear stresses here acting on two edges are always accompanied by a set of complementary shear. So, with respect to these two figures, let us consider this figure 1. It is a block is subjected to shear stress of magnitude tau on two of its edge. Because of this stress, you can see here the rotational effect is to turn this block in the forward direction, rotating the block. There is a tendency of rotating this block in the clockwise direction, and the tendency of rotating the block in the clockwise direction, that is not the equilibrium condition, that is not the desire. So, to keep the block in equilibrium condition, so two more shear stresses are acting on other two faces. You can see the stresses acting here. So, this stress is complementing this stress and this stress is complementing to the top edge stress. Now, when these two stresses developed along on other two faces, they complement the already acting shear stresses on two faces. So, under this condition, the element is said to be in the complementary. So, this process is known as state of simple shear and complementary shear. The shear stresses so developed on other two faces to complement the stresses already acting on two edges are known as complementary, and this entire system is known as state of simple shear and complementary shear. So, this is about state of simple shear and complementary shear. Now, along with the shear strain and shear state of simple shear, let us introduce another elastic constant. It is called as shear modulus, or the shear modulus can also be called as rigidity modulus. And this can be denoted by C, capital C or capital G, both are one and the same. So, we defined and we have used Young's modulus. We defined Poisson's ratio and also we used Poisson's ratio to have various relationships and to solve the numerical problem. In the same line, we can learn what is this shear modulus or rigidity modulus. As per this shear modulus or rigidity modulus, for every elastic material, the ratio of shear stress to the corresponding shear strain remains constant up to the elastic limit of the given material. This constant ratio is known as shear modulus. And as we are obtaining this shear modulus by considering the ratio of shear stress and shear strain, the unit of shear modulus is same as that of again direct stress. So, this can be denoted by C or G. So, hence shear modulus C is equal to shear stress divided by shear strain. Here tau is equal to shear stress and pi is equal to shear strain, just we have defined this one, and C is equal to shear modulus or rigidity modulus. This value of shear modulus again we will discuss little later after defining one more elastic constant. So, we can compare the values of various elastic constant. So, totally we have discussed now till now it is 3 elastic constant, namely Young's modulus, Poisson's ratio and shear modulus or rigidity modulus. So, with these Young's modulus, Poisson's ratio and this shear modulus, now we can establish the relationship. Next, to derive expression for the relationship between Young's modulus comma shear modulus and Poisson's ratio. So, they may restrict only up to here. To derive expression for the relation between Young's modulus and shear modulus, for that also we do the following expression. They may also ask to derive the expression for the relationship between or to show the relationship between Young's modulus, shear modulus and Poisson's ratio. Now, let us consider an element, a square element or rectangular element. Now let us consider a square element. Let this square element is fixed at one end and free at the other end. Write considerably a bigger figure, so that we can mark all the dimensions and all the elements with all distinct clarity. Join the diagonal of the element let A, B, C, D be the element. Again, let this element is subjected to shear stress of magnitude tau at its top edge. As a result of this shear stress, the original position of the element ABCD gets shifted to AB dash, C dash and D, resulting shear strain. So we can see the angular displacement. So we can easily say here it is B dash B divided by AB is equal to the shear strain pi. Now join the displaced diagonal to the original point at the fixity. Now let us drop a perpendicular to this new diagonal from B. Drop a perpendicular and designate this the point of intersection of the new diagonal as call this as point F, A, B, C, D. Instead of E, let us use it as F, because E, capital E we use for Young's modulus. As the element is subjected to shear stress on top edge, so the original position of element A, B, C, D gets shifted to A, B dash, C dash, D, resulting shear strain. Before that, along the diagonal BD, they developed stresses, in the sense resistance, to oppose the displacement along the diagonal and perpendicular to the diagonal to the magnitude of same magnitude what the element is subjected, same magnitude of stress, you can say same magnitude of stress what the element is subjected. So this is tau, you can see here. So along the diagonal and perpendicular to the diagonal, stresses of same magnitude will develop to keep the system in equilibrium. So with this figure and these elements, now we can comfortably derive expression to show the relationship between Young's modulus, shear modulus, or expression for Young's modulus, shear modulus and Poisson's ratio. So after writing this, now let us write the formal words. Consider a square element subjected to shear stress of magnitude tau at its top edge. As a result, the original position of element ABCD gets shifted to AB dash, C dash, D. Next, let capital E be the Young's modulus of the material C be the shear modulus and 1 over m be the Poisson's ratio. Here to maintain equilibrium, state of simple shear and complementary shear will comes into picture, and shear stress of same magnitude will develop along and perpendicular to the diagonal. As shown in the figure. So these are the formal words. Now let us consider the figure again. How you can see here, when the material before subjecting to shear stress, the length of the diagonal is BD. After it is subjected to shear stress on its top edge, as element AB CD gets shifted to AB dash C dash D dash, along with this the diagonal DB gets shifted to DB dash. Based on these linear changes in the diagonal, BD gets shifted to B dash D. Based on these linear changes, we can write expression for linear strain. Linear strain along the diagonal BD is equal to the change in length in the diagonal divided by original length of the diagonal. You can see here, because of this applied shear stress, diagonal BD gets shifted to B dash D, and here conveniently we have dropped the perpendicular. Perpendicular means it is here BD is equal to FD. So the length FB dash will be the increased length. Increased length is nothing but change in length. So this change in length FB dash divided by the original length. Original length is BD, that is equal to FD, gives us the linear strain along diagonal BD. Now, linear strain along diagonal BD, that is equal to BB dash sorry, B dash F, B dash F divided by, this is change in length, B dash F divided by BD. Call this as equation 1. Next, you can see here, as the displacement is very small, AB gets displaced to AB dash, DC gets displaced to DC dash, and here the displacement is small. As the displacement is very small, we can write that triangle BB dash F is approximately equal to triangle DBA, and we have considered the square element. In its original condition, if you join the diagonal, triangle ABD is equal to 45 degree. As the displacement is very small, we can also consider FB dash B is equal to ABD. When we are equating ABD is equal to FB dash B, so this angle measures 45 degree. So angle FB dash B measure 45 degree, already this ABD is equal to 45 degree. So by using these two triangles, we can have expression for B dash F and BD. Next, as the displacement is very small, comma, triangle BB dash F is approximately equal to DBA. Now consider angle BB dash F. If you consider the angle BB dash F and this is 45 degree, angle BB dash F is equal to 45 degree, you can write the expression here cos 45 degree. So this angle is 45 degree, cos 45 degree is equal to B dash F divided by B dash B. So adjacent by hypotenuse. Therefore, B dash F is equal to B dash B cos 45 degree. Now consider angle DBA. Again here cos 45 degree is equal to, so if you consider triangle ABD or DBA, cos 45 is equal to, adjacent is AB side, AB divided by BD. Therefore, BD is equal to AB divided by cos 45. Here purposefully you are writing expression for B dash F and BD. Here we are equation 1 is B dash F and BD in the form. So we got B dash F is equal to B dash B cos 45 and BD is equal to AB by cos 45 degree. Substitute B dash F and BD in equation 1, we get that is B dash F is B dash B cos 45, that divided by AB divided by cos 45, that is equal to B dash B divided by AB cos squared 45 degree. So this can also be written as B dash B divided by AB cos squared 45 is nothing but half. Next, from figure, B dash B divided by AB, what is B dash divided by AB, that we already defined. B dash B divided by AB, again this is angular displacement, and if you consider this triangle, tan pi is equal to B dash by B divided by AB, as the displacement is very small, tan pi is approximately equal to pi, and that is equal to B dash by A divided by A by, it is a shear strain. So from figure, B dash B divided by AB is equal to pi. Therefore, B dash B in place of right current pi into 1 over 2. So therefore, the linear strain along diagonal is equal to pi by 2. Also, shear modulus comma C is equal to, just now we have defined, C is equal to tau divided by pi, shear stress divided by shear strain. Therefore, shear strain is equal to tau divided by shear modulus. If you substitute, call this as equation 2, if you substitute pi in equation 2, that is equal to tau, pi is equal to tau means it is already 2c, call this as equation 3. So tau by 2c, this is the relation for linear strain along diagonal BD. Also, linear strain along diagonal in terms of stress, Young's modulus and Poisson's ratio is equal to, here along the diagonal there develop the stresses parallel and perpendicular to the diagonal to keep the system in equilibrium. Now, so we can write linear strain along the diagonal in terms of direct stress. Direct stress here is this shear stress, that is along the diagonal it is a lateral strain and perpendicular to the diagonal it is a lateral, so along the diagonal it is a longitudinal strain and perpendicular to the diagonal is lateral strain. That is equal to tau divided by E, this is longitudinal strain, minus of minus tau divided by ME, this is again lateral strain. So tau divided by E, it is longitudinal strain, lateral strain is always lateral strain is opposite in nature to longitudinal strain, this negative sign. Further, one more negative sign is there inside the bracket, this indicates, so stresses are compressive in nature. This is for compressive stress and this is for lateral strain. That is equal to tau divided by E plus tau divided by ME is equal to, take outside tau by E into 1 plus 1 over m. Call this as equation 4. Equation 3 is the linear strain along the diagonal due to change in dimension, and equation 4 is linear strain along the diagonal in terms of direct stress and Young's modulus. So, here we expressed the strain in two ways. One is in terms of change in dimension, change in linear dimensions, and again linear strain we expressed in terms of direct stress and Young's modulus Poisson's ratio. So, whether we express linear strain in terms of change in dimension or linear strain in terms of direct stress and Young's modulus Poisson's ratio, so linear strain must be same. Hence, we can easily equate equations 3 and 4. Next, from equations 3 and 4, we get, that is, tau divided by 2c is equal to tau divided by E into 1 plus 1 over m. So, both are linear strain. So, tau get cancelled, therefore, E is equal to 2c into 1 plus 1 over m. So, this is the desired expression. This is the desired expression to show the relationship between Young's modulus and shear modulus. So, this can also be state in like this. So, expression to show the relationship between Young's modulus, shear modulus and Poisson's ratio. E is equal to 2c into 1 plus 1 over m, or E is equal to 2c into 1 plus mu, if you denote the Poisson's ratio as mu.